So, audio should work. Let's wait a tiny bit so I can verify that audio works because no one is complaining. Yeah, so it does. Oh, welcome. So today I was working on the next HDMI firewall, but I'll do a quick introduction because I never presented this project previously. So HDMI firewall, what is it? It all started with a conference where someone presented how to firewall HDMI, and the idea is just pass the audio and video data, block everything else. So because HDMI offers a lot of other interfaces like EDIT, like something like HDCP, it offers also some networking, some USB interfaces. So anything could be hacked. So this increases the attack surface. So you could hack HDMI monitors from your laptop, for example, and then have the HDMI monitor hack back the laptop. That's possible. Or just if it's a smart TV, hack the HDMI, hack the smart TV over HDMI, and then you are in the network of someone else. Because, for example, if you're invited to present in a company, generally you present on a projector, you could hack the projector. If it's a smart TV, you could hack the smart TV, and then you are inside the network, the company's network. Excellent for industrial spying. And the idea of the HDMI firewall is to prevent that. So you can only transfer data, you block all the other interfaces, so you can't hack the monitor. This is what they presented, and the hardware was, they produced some for them, but it wasn't available for everyone else. So I decided to re-implement it based on the research, and it's not too hard. It's just passing the video and audio lines of HDMI and block everything else. With one exception, it's the EDIT information. When you connect over HDMI, you have to read out, so the monitor, I'll say the monitor for now, but very often they are called sync in the specification, but I'll just say monitor. So whenever you connect your device, which is normally called the source, to the monitor, which is normally called the sink, then you read the information about the monitor, what resolution it supports, what refresh rates, and so on. This is the EDIT information. You also have that over VGA, DVI, and even the display port. This is very common for everything else, for everything. And you still have to make this information available, but in a secure fashion. This is why there is additionally an EEPROM where you save this EDIT information, which can be read out, because basically it is an EEPROM, just it's nothing. It can be more complicated. Very often you can just get with just an EEPROM. There are some cases where the EDIT information can have lots of extension, and if it has more than one extension, just an EEPROM won't work. In most cases, it is just an EEPROM because I have never found anything which has more than one extension. So in this case, we just forward the data traffic. This was the first version. You just forward the video and audio lines, and the EDIT information is stored into the EEPROM here. And this worked. This was version 0. Is it written somewhere? Yeah, version 0. This works perfectly fine, although it was radiating a bit much. The issue is that this is not manufacturable because you have connectors on both sides. So not a good idea. It's easy to design. I just wanted to design by hand, and I was not familiar with routing high-speed signals. I didn't route any high-speed signal. The most I did was USB 2. USB 2 is very reliant. It's not really a high-speed data signal. HDMI is 300 megahertz. This is a complete different ballpark with the clock. And this was my first opportunity to route high-speed signals, and it wasn't perfect. It was radiating, so I had to change. But the device works. It's just radiating a bit, so you can listen to it. Something is it called? I don't remember what it's called. Where you can just place an antenna next to it, and then you can grab the video signal. But the prototype was working quite well, so I made the next version, which is this one. This is version 1, and it's a lot smaller. And instead of having 2 times the receptacle, you could directly plug it in the back of your TV and then plug your normal HDMI signal. So it is really compact. Also, this is not really manufacturable because we have component on one side, we have an edge connector on the other side, and we have some parts on this side. Well, it is manufactured, it just costs a lot of money because it's two-sided plus an edge connector. So that costs a lot of money for a small gadget. Still, I did some per hand, a couple, 10 of them, and I put them in the shop. And it worked really well. Within one day, everything was sold out. I don't know why. It seems to be that people were interested into the HDMI firewall. And because it was sold out, and I did the ones I had by hand, and it seems that people are more interested, so I created a new version, which is more manufacturable. So everything on one side and not on two sides. And also I used the opportunity to actually improve the HDMI firewall, because here you have an EEPROM and you have to program this EEPROM with the edit information, which is quite complicated. I did put a manual which allows you to actually write it using over HDMI actually, but mainly on Linux. There are also some tools on Windows, but mainly on Linux, and you still need to be somewhat knowledgeable with Linux programming, Linux tool, Linux command line interface to be able to do that. I also, because of this shortcoming, I also created this HDMI firewall programmer, where you plug it into the monitor, you press the button so it reads the edit information, then you plug it into the HDMI firewall and you press the button for longer, and then it programs the information into the EEPROM. But this means that you had one device for the HDMI firewall, which you either can program using Linux or yourself, and then you have a second device which is used actually to program it. And again, this device is not really easy to manufacture because we have connectors on both sides, we have an edge connector, but it works. So if you want to solder by hand, everything is open source, so even the version 0. You can download them, and you can download the boards. You can even ask for me. You can even ask for some boards. So next time you buy something, just leave me a message and I'll send you a board for free. As long as I have some. But I still have, for the HDMI firewall, I have a board. For the HDMI firewall programmer, I have a board. Ask for one, I'll give you a board with the next time you buy something. You still have to buy the components yourself. There are not a lot of components. They are documented in the BOM, so just download the BOM. Just like something like 10 components. That's it, and then solder it yourself. I won't do it for you. This is just too much work soldering. But this is why I created the HDMI Firewall 2 version 2. This is this one. This is not yet released because it's still in prototyping phase, and this has several advantages. So this is one of the boards. I've already soldered one of the boards. It looks like this, and these are some debugging connectors, debugging cables, and it looks like this. So it doesn't have this plug and receptacle format anymore. On one side, you have 2 times the receptacle. So this one was useful because you just plugged it in the back of the screen, and then you just need one cable, and it's quite nice design. The problem is that there is an edge connector which is not easy to solder because you have to solder on both sides. So this is hand soldering plus hand placement, and this is always other manufacturing. The other problem with that is that if you have a monitor which where you have to plug it this way, this might be a bit too long, and then the cable again would be too long. And the last issue is that once you plug it in the back of your monitor, then you don't have access to it anymore, which is good or not good as you wish, but you have hard access to it. Normally it's not a problem because you only program once and then you leave it here. But to make it a bit easier, because you don't always have access to your monitor, in case you don't have access to the monitor, or in case this is too long and the cable will stick too much out and you can't plug it in the back of the monitor, I decided to have 2 receptacles. this allows you to actually, if you don't have access to the monitor but only to the cable, you can still use the HDMI firewall. And if the cable, if you still just need a cable, so whatever it needs, it works. This is the first improvement or change. The second one was that this was blocking everything except data and had a local copy of the edit information. Actually, not this one. This one doesn't work. This one works. You see, when I did something that works, I put this sticker on it. If it doesn't have the sticker, it means it doesn't work. Here, this one works. So yeah, it cut everything. So you don't have HDCP, for example, or you don't have USB over HDMI, which sometimes is good. But in this one, I made it actually optional. So you can enable again HPD, you can CC, for example, remote control. If you think that this is secure enough, you can still enable it using this dip switch. And using this dip switch, you can enable several things and just block. For example, you just want to block USB over HDMI, you just switch off the HPD and util. These are the two things. If you want CC enabled, you just enable CC. If you want to have HDCP, then you can enable the two I2C lines. So DDC interface, which is two I2C lines, SCL and SDA, you can enable them, and then you have HDCP again. But you still disable the other interfaces, so it's up to you. This is the second improvement, and the last improvement is that now the programmer, which used to be separate, this one was the programmer for the edit information, is now included on the board. So you don't have any, with every HDMI firewall, you can program, you can make a local copy of the edit information. And actually what I've noticed, that's the third improvement. And this is what I'm currently working on. I did finish the firmware somehow, but it's still, I found some bugs. So the firmware here is there, and it can provide the edit information, and it can read the edit information from there. So make a local copy, which is not writable, and it limits the interface to the edit information if you block the DDC interface, so the I2C lines. And I just arrived to a problem. Well, yeah, a lot of small components. Let me get rid of them. I just arrived at a point where I have an issue, is that I can't read two issues. I can't read the edit information, and the microcontroller thinks that the DDC line is not blocked, although it is blocked. So these are two bugs I was currently working on, and I decided to make a stream out of it. This is where we are now, and this is why I started soldering this connector, so we can actually debug the interface and have the DDC interface on both sides. And I need to finish soldering it, and so we will do that and then debug. So this is the 5-volt line. 5-volt line is useful because it can tell me when the source, so the device is plugged. And as device, you won't see everything every time on this small camera, but with the overview camera, this one, you can have an overview look for how I test it and so on. So this is the 5-volt line, and to test it, I just use a Raspberry Pi, and which I connect over HDMI to a monitor. This is an HD monitor. What's good is that video transfer works, so my high-speed signaling is okay. It's not perfect though. On the differential pair are lens matched within the pair, but not across the pairs. I don't know if this is. I didn't read it. I don't know if this is. I don't know if this is a must. That they must be lens matched across the pairs. I will still fix that for the next version. I'll try. I think it works with it works there. I tested with on the screen, and HD works without a problem. It might be an issue with 4K. I don't have any 4K monitor, so I cannot test it. I don't also have a monitor which supports USB, so I can't test does it work if I enable USB. USB is called AMHL. The USB over HDMI. or CC. I don't have any monitor which supports CC, so I don't know if it works. Yeah. I'm a small guy in my just building some gadgets and not a huge company. I can't test everything. But for now, I want to test this. Now we need ground points. This is ground points. Up. That's it. There we have ground. So let's plug back in the programmer, the serial debug, and that I can show you actually the serial debug. The firmware is mostly complete. It's just now these two scenarios which don't work perfectly. We'll put it here. Up. This is more readable. Let me enable the laptop, and here we have the serial debug. This doesn't. That's normal that it doesn't exist. OMAP we don't need. We are not using AT commands. Okay. And here, every time I press on the button, you should see we're in the loop. Yeah. Reading a sync edit fails. It fails because it is not connected. Actually, the LED should go on if it fails. Why doesn't LED go on? This is already something wrong in the firmware. Let me check. Actually forward. So where is this code? The success edits can't read edit ITC line forwarded. Okay, edit forwarded. To master here success. Go to end. That's if success, and if not success, this is here. I won't show you the code. It's not released yet, and it's not really the important part. We will enable the LED. That switch LED. Yep, this is LED on. I want to have the LED on. And LED on is when I sync. Switch LED on to indicate I2C read fail. I2C read fail. Up. Tack. Okay, make flash. Why is it so small? Yes, I know why it's so small. But yeah, ITC fail, and now the LED is still not on. Okay. Is it the wrong place? ODR, this is syncing. No, this should be fine. Read equal edit length, edit, wrong place. Edit success. It's somewhere. No, it's right. Yeah. It was at the wrong place. Fail. Tack. Up. And now the LED is on. Up. This LED is on. It means it fails. This is a pink LED. I bought some UV LEDs and they turn out to be pink. So now when I have a project, I just use pink LEDs. It's different. And I have no idea why I have pink LEDs instead of UV LEDs, but LEDs don't cost much. I won't complain for this thing. So it cannot read the edit information simply because we didn't plug the sync in. So it cannot read from the sync. Normally it is thought that you first plug the sync, the monitor, and then you plug the device or the source, and the device will provide the the other way around here. The device will provide the 5 volts and to start the microcontroller, and since the sync is already connected, it can read over I2C the edit information from the monitor. And let's try again to see if it still fails. Yeah, reading fails. And now we will test why. And that's what we want to do. So we are on these two lines. This is I2C. This is ground. The shell of HDMI is ground. That's one line. That's the other line is green. Let's get the other line. For now, I want to check with the oscilloscope and not with the wrong one, and not with the logic analyzer, because I want to see if the signals look good or not. I need to switch on the oscilloscope for you. Let me switch it on. Oscilloscope capture. Oscilloscope. Okay, that works. So let's start a read and see if we can trigger on it. Yes, we can trigger. So I already see that the I2C. Why does it trigger again? I already see that the I2C. So we see some I2C data traffic, but it doesn't look very nice because we have weak pull-ups on the sync side. I thought there will always between 1 and 2K. I noted in the schematic, so I read it somewhere in the specification. This is not 1K, and I have a 30. This is 30 kilohertz. Frequency is 30 kilohertz or 25 kilohertz. This is not really fast for I2C, so I need to check in the specification. 30 kilohertz. The yellow one is the clock and the blue one is the data. We see there is some data, but it is too fast. So I can decrease the speed, and we will decrease the speed, but I'm wondering why is it so. It looks crap. So the pull-up resistor is not strong. Let me check. I thought in the specification I saw the pull-up resistor should be stronger. Let's check. Get me some free screen. This one. So up. HDMI firewall docs, and I'm based on the specification which is available from HDMI. The 1.3. This is available for everyone to download. I'm not part of the HDMI consortium forum, no matter what they're called. Just a small hacker. So I'm just working on public documentation, and it's only up to 1.3. So, and I don't have any monitor which is above 1.3. So I've never tested it against that. So let's see full screen here. Here we have the specification: physical layer, TMS lines, dual link. Okay, where did I see? So we are using these. Where are they here? DDC. This is the ground for the DDC. Here, SCL and SDA. These are the two I2C lines. Contact sequence. Yeah, mating, vibration, track durability. Where did I see? Let's track resistor. Here, minimum 1.5K, maximum 1.5K is the minimum. I'm using 1.5K because I want fast pull-ups, and the maximum is 2 kilo ohm. This is not 2 kilo ohm. This is far too slow for 2 kilo ohm. Damn it. Okay, now I know why. I didn't read this part. The source pull-up. So normally on I2C, you only have one side which pulls it up, and not both sides. Okay, so I have a flaw in my design. Kind of. No, sync. Okay, yeah. So I have a flaw in my design. Oh, not too important, but actually I don't know. So they also have a flaw in their design. The original guy, which it's the research. Put up the DDC lines. Yeah, that's the DDC interface. This is for STL. So the source is the device. This one has a pull-up resistor, and this is also why I detect that it is forwarded, because how I detect that the lines are forwarded, I just measure if the lines are already pulled up. This is why. And the sync has one dot. So actually I don't even need so strong pull-up resistors. Let's have a look at the original doc. This is the original slides. Parfait pour HDMI. This one? No, that's not this one. This is for high-speed signal. Where are the original slides? Here. These are the original slides, and here they provided the schematic. And here they added a 13K resistor. So whoever did this design didn't read the specification correctly, like I did. I didn't also. And added a 31 kilo ohm resistor. They are emulating the sync, and the sync is 47 kilo ohm resistor exactly. I read the specification wrongly, and I implemented the source. If we have a look at my board layout, here I'm using a 1.5 kilo. And this is actually for the sinks, the source side, not for the sink. And here I'm acting as a sink. So this is already wrong. This I need to fix. I didn't print anything, did I? No, I didn't print it. Let me take a note somewhere. There's also another thing I wanted to fix. What was it? I'll just print this page so I can note everything on the page. Print. So, yep, I'm doing some things wrong. Damn it. That's big enough. So let me write down. DDC pull-up for the sync. It's 47 kilo ohm. For the source, it is 1.5 kilo ohm. So what I could do, because I'm also acting as a source when I want to read the, well, I should rename that, while I read the I2C from the monitor, the actual monitor. And the other way around is just read it very slowly, because it is still a pull-up. It is quite weak, but it is still a pull-up. So just have super slow I2C, and this is what I will do. Do I want to change that? 4500 kilo between each other. How do I want to fix it? Yeah, and in the code, this is I can't detect. So the problem is that I have to detect when. Oh, actually, I know how I can detect it. I just monitor for. No, I can't immediately because I don't know when it will do it. There are several ways to detect. Here we have, this is the dip switch, which blocks and forwards the SDA lines, which are coming from the source and then which are going to the sink. And when this is forwarded, I am not allowed to intervene or to emulate the idiot using this chip. So I need to detect when they are plugged in. Right now, how I detected it is I measured if the both sides are pulled up without me pulling it up. That's how I did, but this is a flawed way to do it, because as we see, both sides have pull-ups. I need to have pull-ups on the other side. Do I plug here? I have, so how do I do it? I don't pull it up myself because I have these pull-ups, this pull-up signal. And so they don't crosstalk. I connecting to 2 pins and then I pull up on both sides. The problem is I don't, oh, I do. 1 and 2, I have 2 pins, so I can also pull up on the other side. So they don't crosstalk. I have exactly 2 pins free. No, I have more than 2 pins free. I'm not using this RX pin. I'm using TX for debugging. I'm not using RX, so I have a third pin for this free. So I could add a pull-up on the source side, sync side, sorry, on the sync side, on the monitor side. I'll add that. Add pull-up on, but I don't need it though. I can really read it really slowly. 47K is not high, but it is still pulling up. So I wouldn't need to add this 1.5K on the monitor side. Add pull up in sync? Question mark. I don't know. Let's change the code. So this is the code and have a really slow I2C. The speed here is the speed here. I'm taking the speed 100 kilohertz. Let's make it 1 kilohertz, so 100 times slower. Super slow, but that's okay. For now, that's okay. I wouldn't like to. It still would take super long. So let's flash and let's see how it looks like on the oscilloscope. Flashing. Okay. Even that is so slow. This is in kilohertz, right? How did I implement it? Tab edit. Soft I2C master.h. Frequency in kilohertz. Yeah, it is in kilohertz. Let's go back to the bench. So it is slow and this is still probably failing even if it's that slow. Let's try to reset. So the signal is a lot slower. It's not even reading. Why is it not reading? I don't have any pull down signal. Sure, it is slow, but it should do something. Is 2 kilohertz too slow and I can actually can't? How did I implement my soft serial? Maybe 2 kilohertz is too. I've never tried. Let's try with 10. The oscilloscope is still triggering. The oscilloscope's probe are still there, so it should still trigger, but it doesn't trigger at all. No, it doesn't. I'll increase this so you can better see the fails. Let's try 50 to see reading sync failed. I think I didn't check where, I didn't say where it failed. I could have a debug code to see where it failed. Maybe it fails because it's not pulled high at the right moment. That's completely possible. So I need to wait a bit longer until it's pulled high. Not possible. Setup. Can the setup? I have to read my software code. During the setup, yes, I have a bool. Return if they're high or not. Okay. Let's have more debugging. So success, it will be not success, but return code. And it will be uint 8t. This is the return code. 0 means it is succeeded. It succeeded. Yep. Check. Check. Let's put it here. If not, I2CRC is equal to 1. That's the error code. Then we go to end. And we do the same for the other ones. 2. 3. The address, that's okay. 4, and this way we know at which step it fails. 5. We still have enough space on the microcontroller. It says this tiny microcontroller. It says STM8S microcontroller. We have 8 kilobytes, and I am at 4, almost 4 kilobytes now, so I still have enough space. So if 0 is equal to I2CRC, else it is here, fail. Damn it, I didn't put the error codes. Fail. What do I have? Do I have a print somewhere here? Print N, print H. Put C. Yeah, I'll have to use put C. Fail. RC is equal. I don't have any string functions. They just take too much space. And we can put C 0 plus I2CRC RC. And put the last part. Check. Up. Let's flash it and let's see where it fails. Success. Who uses success again? 54. Success is equal to true. Yes, it is by default. So I2CIC, let's clear it up. That's not what I wanted. Yes, success. This doesn't exist anymore. Let's write it. We never know. Normally we should write it here actually, and not on the top. But both things are okay. So in theory, if I did everything, I did write it correctly everywhere, but in case I forget to put the code, the RC code, let's do it this way. 7, 8. This way is correct. So in case I forget to set I2CRC to the code, but I still fail and I go to the end, then it still is fine. RC is equal to, so the setup is wrong. And the setup is wrong when the lines are not pulled high. Because they're not pulled high fast enough. I think that's, so yeah, it's I2C master setup. Why did it work? It worked before. This is here, you see, I return if both lines are high, but they are not high currently because the pull-up is too slow. Using open drain. switch between 2 outputs and an open drain currently. So this sets it high, but apparently it doesn't set it high fast enough. I2C delay, get time to get high. Ah, I do give a bit of time. So how long is the delay? I2C delay periods. That's one period. So if I make it really slow, it should be fine. Period is properly defined here. When I do the setup, yep, this is the period. Calculated from frequency hand tunes using 60 megahertz. I don't know how I did that, but probably did it correctly. Doesn't have to be precise, but the period isn't long enough. Let's try again at 1 kilohertz. Let's hope that at 1 kilohertz it's good enough, but my design is flawed. No, still not enough. Let's have a look at the oscilloscope. You don't see the code currently, but it's not too important. Oh, okay. That's weird. Line 1. So line 1 is pulled up, but not the other one. Line 1 is the clock. The clock is pulled up, but the data line is not pulled up. Why isn't the data line pulled up? Oh, wrong one. That's this one, the green one. Why isn't the data line pulled up by the monitor? This is weird. You could have told me. I wasn't seeing the oscilloscope screen. It should have a pull-up. It seems it doesn't have a pull-up. Maybe it doesn't when it's not on. Let's switch it off. No, because the clock line is pulled up. Okay, this is on. The monitor is on. Now it is pulled up. And I think when it goes to sleep, it is pulled down. This is weird, but totally possible. No, now it is sleeping and it is pulled down. It is pulled up. I have no idea why this happened. I do provide 5 volts. This is really weird. Now if I read it, yes, okay, I2C now works. It is super slow, but it works. It takes forever. Yeah, saving it done. Whoa, this is super slow. The code works. But you see already the pull up is, we are at the limit here. The pull up is still very slow, but it's because my design is flawed. Yeah, but I2C now works even if I don't pull it up myself. But the detection, so this is one bug fixed, and the bug is in my design. Properly, I have enough pins in my design to pull both sides high or low. So to detect if they are interconnected, I have to detect high and low. Not changed, okay. Not changed, okay. I don't know what happened with the serial now, not too important. That's one bug fixed. Let me commit the bug. Git add -p. Oh, this is UART. Yep, let's save this. Clear tri-state, wait shortly to clear tri-state. Okay, this is another bug. I don't commit this, I don't commit this. I will commit this. and I commit this. Why do I have this? Yeah, I2C transaction, I don't care anymore, but that's for later. Git commit. You're not seeing what I'm doing, it's not too important. Improve I2C master debugging. Debugging, that's done. Okay, I still have one more commit. No, that wasn't this. Damn it, I did commit two things at once. Nobody will care about my commits. I'm the only one to look at my code. It's not too important. I could revert it and then do it differently. Nah, I don't care. Not, yes. Remove unused debug. This is another thing where when it compiles, it optimizes a bit too much and it complains that I have no code. That's done. And now we need to fix the detection of I2C. And now it's still high. Why wasn't it high for a long time? Maybe I did change the code and pull it low. I know. No, I don't. Because I reset the microcontroller. The microcontroller should have put it low. Should put it high again in open drain. So I don't know. But now I need to fix that, how to detect if the I2C lines are forwarded or not. That I need to change. And how I change it, a bit of a pain. And I don't know if I'm allowed to do it. I am allowed to do it unless... So, how it works. Let me show you the schematic. Full screen. On the schematic here, we have this presence detection here, which is on HPD hot plug detect. I think that's what HPD is there. And it is there to indicate that the monitor is there, or the sink is here. And when this is high, then you need to be able to answer in an I2C fast enough. The problem is when I connect, I think I still have a bit of time, that's okay. Problem is when this is forwarded, I don't control. So if this is not forwarded, I control when it is pulled up using this presence pin, which goes to the microcontroller. So I can enable really late. And while the hot plug is not detected, it will not read the I2C lines. So I can do whatever I want with these I2C lines. The problem is if this is forwarded because of this switch and they want to forward it because they're using, for example, USB, I can't control it, meaning that it will be pulled up by the sink itself, and I don't have, so I can't control it, meaning I probably don't have the time to test the I2C lines, but actually I do. I have 20 milliseconds. Only after the 20 milliseconds after the hot plug detect is high, it will start to read the pull-up. So I need to do it within 20 milliseconds. And I think the microcontroller is fast enough to do it. I didn't measure it. This is something I need to do. But that will be the solution. So in the code, we will do that, configure I2C pull-up. And actually I will change and I will have more pull-ups. I will have 4. So 4 pins just to test the I2C pull-ups, just because I want them to be forwarded for HDCP to work. But luckily I have these pins 3. So it's okay. It's not ideal, but it is okay. Although we see it worked with 1 kilohertz, it's just super slow, but it works. So do I really need to do it? Nah. I have pins. I have spare pins, so I can do it. Should do it the proper way around. How do I do it? I have to use the SDA lines myself and then pull high and low and tests. Let me check. Here I have the SDA pull up and then I have SDA here. Okay, so I just need to pull up these two lines and low and check if they're on here. I could also do it here, but the problem if I do it here, no, it's not really a problem though. No, I could also do it here. I just don't do it here. I have already this configured. So I will pull low and high here, and I will measure if it's low and high here. And if it's low and high, and actually in this order, I could have also a pattern like low, high, low, and then if it's the same pattern, then they're connected. They are pulled up. So if I pull, they are pulled up no matter what actually. So if I pull it low, and if they are low here, then they're interconnected. But the problem is to check if they're connected to the monitor. And if they're connected to the monitor, they're not connected, they're probably not high. I just want to interconnect both of them to check the connection between both lines if they're forwarded, so I don't care. Yeah, I'll pull up high, low, and then that's good enough. I could do high, low, high. That would be the proper way because I don't know if it's pulled up fast. Yeah, high, low, high. Although high, low is good enough. Yeah, high, low is good enough. The problem is if the source, so the real device, also pulls it low within these 20 milliseconds. If I do high, low, high to verify and it pulls it low, then it won't work. So let's just do a high and low and not just high, because high we see it doesn't work. So here are OpenStrange pull low. And actually I already pull low. That's weird. But I don't verify on the other pins. Check if pulled, if forwarded true. Why do I check? Check if it's pulled up. I shouldn't check on this pull up. I should check on the SDA lines, not on the SDA PU lines. My code is buggy right there. Yep, it's buggy right there. Why did it work with the other one? This already worked with the other plug when it's not plugged to the monitor. It pulls low. It switches to inputs. Then it verifies. I'll remember how I do it. I did it the other way around. What I did is I did pull these two things low. And actually then I measure. If it's high, it means that someone else is pulling these two lines up. And I expected it that it was the monitor, but actually it's not the monitor, it was the device, the source, which pulled it up. And this is wrong because the monitor can pull it up. So this doesn't check the forward. Okay, this is why I didn't check this way. Got it. The problem is that now, how do I check if it's pulled high or low? Because we have the monitor, the source, which also pulls it up. I actually don't even need these things because the source pulls it up. I could have 40, yeah, I don't even, do I need them? It says in the specification, it says that they need to be here. So I will put them because the specification says so. Why do they, because generally you only need one on one side, the pull up. Why do they have this pull up on the sync side also? This I don't know. ICS actuator, long timing, blah blah blah. It's not written here. Hot plug detect. Okay, this is something else. DDC electronic configurator. I don't know. I don't know why they put it up here on the sync side. Maybe so it's not noisy. Probably. But then why 47K? Not what? Why not 100K? Meh. I don't know. So to actually test it, what I could do is not pull this low, because if I pull this low, we will have a voltage divider between this one, and this line might not be low enough for this to be detected low. So what I will do is pull these lines low, SCA and SDA, and then I will check if on this side they are also high and low. And based on that, I can figure out which one, if they are forwarded or not. But I didn't define the pins for that. So let's do this in the code and have, I think even these ones are not defined. I will also rename, not M like monitor, but SDA sync and SDA source. Because this is a sync, this is a source. It's just that nobody uses sync and source except, so if you talk to someone not familiar with the HDMI specification, they don't talk about sync and source. Talk about device and monitor. It's easier. But in the code, we can do it properly. And I can copy it from here because I defined it here. So at least it works for now. It will need. So let's put the definitions here. Forward, okay. This is not SDA. Do I call SDA sync or sync SDA? I should actually call it as it is called in the schematic, like SDA M, like SDA monitor, but I will change the schematic. So let's call them SDA sync. And I will also have different pull-ups for different lines for the pull-ups for the sync and the source. Actually, I need to check. I want to use PA1 and PD4. I need to check if PA1 and PD4 can pull high. Doc, datasheets. This one. It's here. Let's put it there. Okay, here we have, no, this is the reference manual. I don't want the reference manual. I want this document. I want the data sheet. Pin block diagram, pinout description. The pinouts are the same, and I know there's one pin which can't here. True open drain. What is that? Not true open drain. High sync capability. Okay. Let's have a look. PA1, it can do push pull. Okay, it can do open drain. And PD4, let's have a look. PD4, where are you? PD4, open drain and push pull. We want push pull because we want to push high and low. Okay, it can do that. So I can do this in my schematic. I can change that and use these two lines or any other lines for that. I also need to rename this one. It says this is an error LED. Why? It's not always an error LED. It's, well, different things. So let's call them correctly. And it will not compile, obviously. So let's change this to STA SSC. Sync is SNK, I think. I'll try to keep it short. Think pull up, change it everywhere. Do the same thing for SCL. And instead of sync, because we want it to be as long, let's put SNK, sync and source. Pull up for device facing, nope. Nope. This is not the case. I2C. Pins, sync and source. These are the pull up, and then we also need to define the not pull up. So for now I don't have the pull up for the other ones, but that's important. And they are on SCL PB4 and PB5. SCL PB4 and PB5. Now I can do the correct checks, and I don't have the pull-ups for now. I can already code them, but without having the board, I can botch them. Won't be a bad idea actually to botch them. The next, I have enough boards. I will do it in the next one. I will have wires. Is this so? These are not connected. So yeah, I can botch them. That's for the next, not next prototype. I want the next prototype, but for the next board, I will actually solder that. But for now, I want to do the detection. Duration timeout. It's not for here. Okay, let's go back to the part where it tests the forwarding, which is somewhere here. Configure I2C pull-ups. So we don't configure the pull-ups for now because we only want to test the forwarding. And to test the forwarding, we will not pull it up. We will have to configure the STA lines. So they're pulled up by definition by both sides. So this detection is wrong. Test I2C forwarding, and I need to release the lines afterwards. Which ones do I want to pull? It will be better if I actually, let's have a look. It will be better if I use these lines to go high and low, because here is the sync side. It's not too important. And then I check if they're high and low here. Then I know that they are forwarded, because if I put high and low, there is a tiny bit more risk that it would conflict with what the source is doing or the device is doing. If it's connected through, it can mitigate, could cause a problem, but it's within the 20 milliseconds. It's short, probably not too important, but I'll still do it for the best case scenario. Do not pull up. Switch to output, switch to open drain. Yes, switch to open drain, both things. Pull line low. Well, for now we test if it's there. It will be high on both sides. So Okay, this on the source side, I switch to open drain and I don't pull it low. So let's already write that I don't want to pull it low. Release SDA line. This is pulling low, this is letting high. Switch pin to open drain. That's okay. And actually, let's do it the other way around. So let's pull it high, let's switch to open drain, and then let's switch to output. The correct way to initialize it properly. And we need to do the same for the SCL line. SCL, and this gives time also for the SCL line to be pulled up, although what happens if it's not connected? No, it should be connected. This will be a requirement. I will say that the monitor must be connected before. I can detect if the monitor is connected or not. That's good. This is another thing. So I had a problem is that I couldn't test, well, I can't detect if it's connected or not. I can't in all cases. So the issue I had is I will read over the I2C the monitor, but it only works if it is connected. So how do I check if it's connected? Normally you use the hot plug display. I can still use it. No, I can't use it because I don't have a pin going to this hot plug display on this side. I only have one which is on this side. Here. There I can read if it's connected or not, but this goes to the source and not to the sink. So I could read it if both lines are, so sink or source are connected, if they're not blocked. But that's not all the cases, so I can't rely on that. I could read here if it's pulled up. So what I do is I put it low. I read on this side if it's low. If it's low, it means that, yeah, if it's low, because I only have 5 volts coming from the source. So the source will have pull these two lines low, high, using its pull-up resistors. So if I pull it low, here it also pulls. If I pull it low, it means that these are interconnected. Then I pull it high again, and if I put it high, it means I leave it on, and if I read if it's high, it means that this is connected to the open drain after some time. But it might also be that they're forwarded, so they're connected to the things like here. So I can again pull low here. Yep, that's how I will do it. I will pull then low here. If it's still low on this side, they're interconnected. If it's not low on this side, so then I cannot test if the monitor is there or not. But I know it is interconnected, so I don't have to test if the monitor is there because I don't want to mingle. And if it's not forwarded, then this will go high while this is low. It means that the monitor is here, and I can read over I2C. So this way I can detect if the monitor is there. That's how I'll do it. Yep. That's how I will do it. I can also already put them, so the input register is not the same than the output. So I can also already configure this one as output in open drain, and I leave it high, and I can read the values which are in here. That's what we will do. So first we test, this is the first side. We release the pins, okay. Pins are released, STL, this is the correct side. This is the source side. And I should do the same for the sink side. Yeah, let's initialize it first. Yank. paste, and then this is the same for the sync side. No, I know in Vim there are ways where you can change we can change blocks. I just don't care. I forget all the time how to select the visual blocks and how to edit. I'm not a Vim guru. Just like Vim, because it works in a terminal and it works in every terminal. It's small and it is powerful. So release the lines. Okay, so now both sides are initialized correctly. And actually I should fix the initialization here also. Ensure clock is... Oh, I do already. No, not correctly. This way. You first need to tell, although it's not, yeah, it might be important in OpenDrains because it might be not pulled up to 5 volts but to 3.3 volts. And if you push pull, if you're not in OpenDrain but you are in push pull mode, you might pull it up too high. Not pull it up, push it up too high. So this is the correct way to do it. Although these are nanoseconds differences between both of them, so I don't think it even matters. But yeah, let's still do it the correct way. We want good code. Test IC forwarding. This is configure. Now we test IC forwarding. First we configure I2C lines, sync and source sides up. Now we test the forwarding and we tested how I defined it. So we switch this low. Release takes, and this is SCL. SCL and release, not release. Yeah, yep. We can do it this way. And this is SCL. I actually could do on only one pin, but I want to test on both pins. Yeah, because if only one of them, any one of them is connected, I can't intervene. So I need to test both of them. Assert line, and we assert it this way. We will assert both lines. It gives time to be low before we read them. Although when we pull low, it should be immediate, but we'll still do it this way. Tack. So now I read if so we are sync source syncs. We are asserting on the sync side, not on the source side, and we will check on the source side. Sync. I need to define because I am a. No, we assert it on the sync side because I will play the source for this, but this is the sync side. Did I configure it correctly here? Yeah, source PB5, right? Source PB5, that's correct. Okay. Sync PD2 and PD3, PD2 and PD3. Yep. And actually for these lines, I have to use, I can't put on any GPIOs because I need the I2C implemented in the I2C interface implemented here. This is software I2C. I can't put it on any line. I will be back soon. I need to do something shortly. Wrong one. This one is the correct one. Okay. So this is done correctly. Now I need to test on the source side if they are low. So if 0 is equal on the source side, IDR, and first the clock, because this is the one we are set at first, or same for the data line. SDA and SDA, then I2C forward is true. Now why did I want to pull these low? I don't need to. I don't need to. I can leave these high. Now, now I will put this one back. I will release them, and if they are high, then it means that they're pulled up by the monitor. Else, this is another thing where I can detect the presence. Ideally I would detect it using this line. The problem, the HPD line, I still have one pin free. The problem with this one is that this is a differential line when you are using HAC+. I think this is USB. HAC+ is, I think it's USB. So these are differential lines, and there's already a pull-up on one of the data minus line. I don't know if I can add a... I don't want to have a trace going there from one of the pins to measure it. That would be the correct way to do it, but I can do it this way. Yeah, so let's do it this way. I actually have to, no matter what I do, I have to pull them high again. So on the sync side. Release. And since it's super weak, I need to wait some time. How long do I need to wait? The oscilloscope is still there, so let's check on the oscilloscope. How much time do I need to wait for it to be pulled up? Reset. Tick. Yeah. So I need around 100 microseconds. Oh, that's okay. It's not too slow. 100 microseconds. That's, I could even, let's check. 50 microseconds. 50 microseconds is enough. Let's wait 50 microseconds because we want to wait as little as possible. Let sync 47K pull up take effect. But I only want if it's not forwarded. I only want to wait and check if it's not forwarded. If not forwarded, else I can skip that and make the code a bit better. We wait and we check the pins again, and we check these pins. And normally, if they're not pulled up, they should still stay low because I don't have any pull up. So this is 50 microseconds. It's microseconds, right? Yeah. The oscilloscope shows microseconds. You didn't see. Let me show you the oscilloscope bench here. On the oscilloscope, you see that it's pulled up in 50 microseconds. So let's go back to my screen, full screen. This one, yeah. And let's go back to coding. If sync, if one of them is low, yeah, we still one of them because both of them should be high. SNK, that's okay. Then we are sync present is equal true. This variable doesn't exist yet. So we need to add it. Static. And it's actually sync present is equal false if the sync is present. Tested using DDC. Sync DDC. Tac. Okay, that's correct. That's correct. Now we need to do the pull-up correctly. So the pull-up, configure I2C pull-ups. We need, okay, this is switch to output, switch push pull. Yeah, exactly. If we don't forward, that's the way to do it. If we don't forward, else they are floating input. By default, they are floating input. So if it's not forwarded, then we need to pull them up. using 47K and not 1K. That needs to be fixed, but we need to do that. So we switch to output, switch to push-pull, and we actually need to do the other way around. Do it correctly. Higher isn't really important in this case. Okay, and then we have here, this is the presence detection, we don't care. Here, edit protected, can't read, reset watchdog, reading sync and only, okay. If I don't see can't read lines. If sync present, wrong. Then we have the last else. And we also indicate the error. Yeah. Sync not present. Up. Let's flash it and let's test it. Flash. Okay, it flashed and we need to see the debug. Sync not present. Yeah, it's too fast, I think, because it is present. And we see in the oscilloscope, here I cannot show you the oscilloscope here, but on the oscilloscope you see the small dip tick, and it should be 50 microseconds. That should be fine. Let's just increase it a tad, because this is not a precise weight. This might not be 50 microseconds. So let's just increase by 1. Let's test again. Sync present again. F0. Ah, damn it. Wrong way around. So the 50 microsecond might have been enough. 50 microseconds. If it's low, it's not present. So if it's high, and if it's high, then the sync is present. Why does it take so long to compile? Ah, okay, because of OBS. Loop changed. Oh, that works now. Let's flash the EEPROM to just invalidate the EEPROM. EEPROM, tac. Okay, it's invalidated. And now if you reset, it should read the EEPROM. Actually, it did it. And it works. It's super slow, but it works. And it's not too important, because normally the EEPROM you only want to read it once, and then you don't want to read it afterwards. And the multimeter still doesn't work. I need to debug this code, but it's painful. Well, it's not too important right now. I can do it by hand. But I really need to debug it. Okay, so we are done. No, we are not done, because now we want to detect if the forwarding has been done correctly. So we disconnect the oscilloscope. Let me switch back to the view, and now we can do, and we don't, yeah, I'll leave the other screen on. So now let's connect this cable. I think, yeah, that cable. Let's connect the Raspberry Pi and check if it still works. Data is not forwarded, so normally if we plug it in, the screen doesn't go on, which is not a good thing. Why doesn't the screen go on? If I connect the screen directly, does it go on? That's my main case, so that should be taken care of correctly. If I connect the screen, entering power save. No, doesn't go on. Okay, it's the, let's move this. It's just the Raspberry Pi which has gotten into sleep probably. So let's try the other way around. Let's still connect this here. Let's connect this to the Raspberry Pi. Let's disconnect the power. The ground might not be perfect, but for UART it might be enough. We don't want to read the edit, so let's switch off edit reading. Let's enable power and let's see if it works. Edit protected. Okay, this works. And HDMI should work. Entering power save. I did something wrong. The SDA lines are released. No, it does. Okay, okay. It just took time. Okay, and see, the screen is on. It means that the HDMI works, and it didn't complain. Will it complain when I do it, when I connect? So is forwarded? We didn't test if forwarding is detected. I2C lines. Okay, we have to test if it can detect the forwarding. So these are this. I can't. These are these two bits here. 1 and 2. And now we unplug, so it doesn't power. And then let's try with this thing. Can't read edit. Why do you want to read the edit? You shouldn't read the edit. I2C ready? Okay, you can't read edit lines forwarded. Yeah, but you shouldn't read them because edit is disabled. Yep, edit is disabled. Why are you getting in this state? Let me get the code. Edit protected. Actually, the edit should be detected as protected. Why didn't you detect it as protected? Enable pull up. It's too slow. The pull up is, I need to wait a tiny bit. I need to wait a couple of, it's 40K. Okay, I need to wait a tiny bit for it to pull up. Let's try this way. Wait for pull up to take effects. I don't know if 10 microseconds are big enough. Let's wait 20 microseconds. Wrong. I need to program this. Okay, now we detect it as protected. That's good. Let's try again. Protected. Protected. Okay, 20 seconds to microseconds is good enough. Can I shave off and then test with 10 microseconds? Every microsecond counts during 21st milliseconds. Programming, edit protected. Yep, it seems to work. Let's try again. Edit protected, yes. And when we unprotect it, it should read the I2C. So let's unprotect and let's reset. ID lanes forwarded. Ah, okay. It detected that they are forwarded. That's good. But actually, why? Okay. It detected that they are forward because the other one was pulling it up. That's good. That's good. If only one side is there, detected that it's forwarded, and because it's forwarded, it can't read the things. So let's do that. Let's try again. Reading edit, that takes forever because we had only 1K, but it works. I'll fix that on the new one. I also didn't add the reset button. Reset is so useful. I have so much space on this board still. This whole connector, for example, could be done, but yeah, not important. Here I have it. Let's try with... Now the edit is programmed normally, so let's try the case. We unplug power, and now we will plug the Raspberry Pi. It's still on. Okay, it's still reading the edit, not change. Okay, and it works. They are not considered forwarded. And now, if it's forwarded, let's forward these lines. Switch off. Switch on. I2C can't read edit. Forwarded. But yeah, okay. You shouldn't. Okay, that is detected correctly. Let's plug off. Let's plug in. I edit protected, so it doesn't test if it's forward. Ooh, but actually, it might be nice to still say if the lines are forwarded or not for debugging. That's not too important. It might be. Yeah, I still want this debug information. Debug information can be removed. Sync presence up here. Puts I2C lines forwarded. Up flash. Do you detect it? Error. Can't open USB device. Yeah, sorry. The programmer wasn't plugged in. Up. Up. Now programmed I2C lines forwarded. I2C ready. I2C ready. I should tell which I2C is ready. I2C is ready is on the other side. I2C source ready, but actually we don't need I2C source if they are forwarded. Source. Because it's not enabled. If not forwarded, because we only initialize the I2C slave if it's not forwarded. So we only want to test that. If not forwarded, then you tell that. Okay, now it doesn't say that. Okay. It doesn't say that I2C is ready because the lines are forwarded. I2C lines are forwarded. DDC. Yeah, I2C lines. I should just say DDC forwarded instead of I2C lines. That's okay. Yeah, the proper sync would be DDC instead of I2C. It's okay. So it works. The HDMI version 2 works. It needs a bit of tweaking, and I will do another. What time is it? Yeah, I still have a tiny bit of time. I can solder the next one with the correct fixes. So we can try the firmware. And I have a bit of time. Maybe you're interested. How long has the stream been going on? Yeah, 2 hours. That's okay. You still have time to watch. If you didn't want to watch, didn't watch. But that works with this. What I didn't test, but I didn't test with the screen if it's not the emulation. I tried the edit reply. I tried, it works. So let's disconnect everything. I will leave these debug connectors here because you never know if I need to debug it again. And this will just be a debug demo part stack, but I don't need this anymore. So this goes in my HDMI. Yeah, I still have so many. So I did build more of them, but the solder paste was old and it created shorts under this HDMI connector. So I had a lot of defective HDMI firewall version 1. That's a shame. C'est la vie. This quality test passed. These are not quality test passed. Up. Yeah. So solder paste, don't. 6-month-old solder paste, don't use it. It's too bad. If you want to play with, actually, again, these are defective. I won't use them. If you want one, ask for one. Don't expect anything, but if you are ordering something in one of these HDMI firewalls, the only problem of these things is here under this connector there are some shorts on these ones. If you want one, I'll give you one for free. Just ask for it on your next order. But don't expect me to debug them or to help you debug it. Take on your own. So let's solder the next one. Do I want to solder those SMD parts first or the connectors? Difference. Oh, it's the SMD part first. The connector might be a tiny bit in the way, and this way I can also solder the resistors somehow. So soldering iron, and then I just those things. I need the parts. I have most of the parts. I don't have them all. Soldering tray. Tack. For now, I can leave it here because I will need it this way. Okay, and I will change also the pink LED. And I added, so you probably didn't see it, I added a footprint for the EEPROM because I wasn't sure that my EEPROM emulation or that my edit emulation was working correctly. It is working correctly, which is fine. Else I will just read and then write in the EEPROM like I do in the previous version. But I didn't need to. I need some fine tweezers. They are here. This is my soldering iron. A bit of space, and we can start with the microcontroller. The microcontroller. It's here. I could use, instead of an STM8S, I could use the Nuvoton N65E003, I think. I would just need to have to rewrite the code and all the registers and so on, so I didn't want to. But they are pin-to-pin compatible. They require one less pin, which is quite good. But yeah, this one is good enough. Doing super high production. So the cost saving might not be super important. Where's my here. Solder wire. So let's just put solder first. Let's put the chip. Not perfectly aligned, but good enough. Since we will do drag soldering and the pitch is fine, let's put some flux. So tack the other side. Okay, the other side is tack, so I can now correctly solder this side. Too much solder, but it just wasn't flowing correctly. Yeah, it's not aligned, but is it fine enough? Yeah, it's good enough. Not pretty, but working. Okay, then the capacitors next to it, which are most of the parts. We have 100 nano. It's this one. I almost know this by heart. Have this one. Here we have this pull-up. Here there are two pull-ups. This I don't need, this I don't need, this I don't need, this I also need. So we then have one microfarad, we have two of them, so one for VCAP, so the internal voltage, because although this microcontroller can operate at 0.3 and 5 volts, internally it operates at 1.5 volts. Soldering handle is too warm. Yeah, it wasn't soldered correctly. Okay, the last 1 microfarad, it's this one. Then I need some for the LED. I will use 10K. I don't like super bright LEDs. I used 1.5K before. Let's use 10K now. I think it's bright enough. We'll see. That's 10K. We have 47. Do I? I don't have 47K, do I? 34K. I don't think I have 47K resistors. So the LED first. So we have pink LEDs. Up. The tweezers are glued. So where is the marking? Here. Okay. This I don't need, this one I don't need, this one I don't need, this one I don't need, and they need to be 47K. Let me check if I have 47K resistors. I think above 10K. Nope. The closest I have are 34Ks. Yep. So many. I have already 3 boxes, just 03, 06, 06, 03 resistors, and every time I start a project I need yet another reel, because some resistors. Pick and place machine. I think when you have an industrial line, you have 3 pick and place machines just for resistors, because you have so many values. And each pick and play machine has probably like 20 or 30 reels of resistors. So we won't have 47K, which is the mandatory. Maybe I do. Let me I have a resistor book. Let me check if in the resistor book I have 47K, because it's a common value. Inductor, capacitor, resistor, 0603. Okay. 603. No. 30. That says not K. This is 1K, 6K, 7K, 51K. 51K. This is closer than 37. The 30. And it's plus minus 20%, I think. I don't remember. Is this 20%? 47, 20%. 10, 8. Yeah, it is within 20%. So this it will be correct. It's even within 10%. So let's use this 41Ks, 51K. We will be spec compliant. Hup. Okay. All SMD parts are sold almost. Do I first sold? Yes, I think I soldered the connectors first. Where are my display connectors? Display connector. Here is my box. We need 2 times HDMI. That's display port, that's not HDMI. This is HDMI. 1 and 2. These are a pain to solder. I don't know why. So first I solder and tag these pins, some of these pins, because it's still wiggling quite a lot. So because of the wiggle, it could be misaligned. It seems okay aligned. Let's tag some pins, and now I can solder the back. I can do it. I can do the other one also at the same time. This it's not perfectly. Let's tag it also on this side. Oh, sorry. Flux, so it flows underneath. Okay, pins are tagged, so I can solder tabs. Okay, now that the tabs are soldered, it's fixed correctly. We can solder the front pins, and it is still aligned. Yeah, it's still aligned. There should be enough solder. Maybe there's enough solder. Needs a lot more flux. These pins are super hard to solder. Not sure that shouldn't be corroded because they're not that old. Okay, with flux makes it easier. Okay, that was one side, that went smooth. Let's do the other side. Flux. Plenty of it, as long as we clean it, it's okay. Although we can't completely clean it because some will go under the pads. Okay, I have too much solder. Let's try to drag it on the pins. Ah, I forgot one resistor. This pull-up resistor. It's 1K. Let's put the percent. Let's put a 1% or 0.1%. 1%? I don't remember. 1K, 1%. That's the most precise I have. Sure, 5% are good enough. It's one side. That's the other side. Now we can put almost the last part, the two last parts. Oh, there are more. Let's first add the dip switch. Dip switch, here you are. Look. They're huge, but I mean, the connectors are huge, so that's okay. Could have a smaller dip switch, but then I cannot go through the pads, which is bad. Because I need to get through the pads for some of the lines. Although I probably don't need, I could also do without, but I have the space, that's fine. This chip needs to be on the side. don't know if it could be in the middle here, if this dipshit would be smaller. But I don't think it's too important that the size is super small. It's meant to be stored somewhere. Actually, I need to first my pad, then get this, and then align it. It's meant to be stored away. And I don't think there's any space problem when you lie. Yeah, it's half more than the cable. I think the space is too much of an issue. Looks okay. Debugging. Oh, I shouldn't do that. Debugging connector. Because we will still flash it and debug it and test if it works correctly. That's debugging connector up to here. Tack. Tack. Okay, tag. Now I can align it correctly. Yep, it's aligned. Okay. That's done, and then we just need the 2 other pins and the 2 other wires. So we need 1.5k resistors, which are here. 1.5k, 1%. Them, and we need them on the SCL lines. So let's make this solder go up to here. Oh, I can actually solder it this way. I have enough space. That's one, and that's not 2. This is 2. And now we will use some magnet wire to connect them. I don't know where to yet, but we'll find it out. Up. This needs solder. Okay. That's one. So which pins can we use? Which pins are unused? We need pin 5 and pin 1. Wow. So let's make this pin 1 and the other pin 5. Pin 1 is here actually. Should I clean afterwards? Yeah, I'll clean afterwards, but I'll be very delicate. Up. see if I managed to connect it on pin 1. Did we say 4 or 5? I think I said 5, but in my mind I have 4. No, it's 5. That's the first one, and let's do the same for the other one. If pins, we could actually have a transistor which enables power to both of them. No, we can't. Yeah, we would have 2 transistors connected with 1 line. Yeah, this we could. We have the pins, so we don't need to save them. In case I do, for any extension, could use transistors. This may be a bit too long. Okay. Strip off the coating of the magnet wire and then try to count 5. 1, 2, 3, 4, 5. This is 5. Oop. Yep. Let's see if it's 5. 1, 2, 3, 4, 5. Yes, it is on 5. Okay, let's clean the board. Let's try to flash with the normal code, and then we will extend the code to cope with these new pull-up resistors. So drops of alcohol, plenty of alcohol. Till this works, we can do the bottom. Let's get some wipes and rub a tiny bit to actually absorb the residue. Okay, same here. I just need to pay attention on the wires. And I'll blow on the thing. Yep, because there's plenty of flux underneath the dip switch and very probably underneath the HDMI connectors. Does this look okay? Let me buzz it. One probe, the other, continuity. Let's buzz and see if it's connected to 5 and not the other one. 5 and not 4. Okay. Connection is correct. Let's connect this. The reset button. Do I want it? Nah. Just plug and unplug if I want to reset. Which one is RX? RX is the blue one. this way. Now we can flash and debug it. One and two. Thank. Yep. Let's flash it. Up, make flash. It flashed and it says, yep, I2C lines forwarded. EDI protected. I2C lines, are they forwarded? No, they are not. Maybe the detection is wrong. They are not forwarded. Let's flash again. Let's try again. I2C lines forwarded. This is not good. Let's wait. I don't know if it's because of the new resistors, which make it a bit harder, or if it's because of the wait time. But when it's not connected to the sink, it cannot tell if it's forwarded or not, because they are not pulled up. That I didn't think about, but it's not too important. Let me think. They are not forwarded, but they are this way because they're not pulled up because the monitor is not connected. But if the monitor, yeah, it's just forwarded or unconnected. I think I could be the same state in both because I would need to pull up. But they're not forwarded. How do I do that? How do I do it? Do I want to pull them up? Do I want to pull them up using the pull-ups? But these are quite high pull-ups. At least for the forwarding, it's important to test, and it would not affect. Yes, I can do that. I can initialize the pull-ups and pull them up. Once they're forwarded, I can still pull them down. Would it be an issue? No, because it adds just a 1K, and there's already a 1K. It's not too much of an issue. Yeah, let's fix that. But I need to define which one is which one. So on pin 1 we have SDA pull-up. So let's switch in the code. Let me get wash my hands to remove the lead. Yeah, we need to pull them up to test if it's, but no, I can't because I want to test if it's present, then I need to pull them down again. That's a pain. So I can test if it's forwarded by pulling it. No matter what I do, I can't pull up the 47Ks. On the source side, I can always pull them up in the beginning. Because it's yeah, I can always, it doesn't add a lot of flow, but it's not completely correct. No, I always have to pull them up. except when they're connected, when that is forwarded, then I can remove them. This is within the 20 milliseconds I can, and I will. So I know that they're forwarded if they are low, and then when I switch up, wait, no, what's happening? I assert the sync. I don't assert, no, I know. I need the other ones to be forwarded to be pulled up high in the beginning to actually pull them up afterwards. Such a complicated case, although it's not probably not important, and I can pull them up and it doesn't matter. It's because it wasn't the wrong side, it was the wrong side. There are 47 cases, so yeah, I can and I will pull up. I will pull up on the source side all the time. Not all the time. Yeah, I will remove the pull up if I notice that they are forwarded, but at the beginning I can leave the pull up. It's not too long, and it is actually, it needs to be meant to be connected. Now I know why this doesn't work. Normally the board only wakes up when it is powered by the source, and the source pulls these two lines up. Here we don't have any source. This is why it detects it wrong. If they're forwarded, we just add 47K. So yeah, this is not a case which is really important, because if we do it correctly, yeah, it's not a case which is really important. Right now, it is wrong. Lines are not forwarded. Also, they say that they are forwarded because I can't test correctly, because I'm not in the rest test scenario. So it's not too much of an important case. I could still fix it by pulling up the source side. It pulls up at 47K. It's not too much of a problem because the 47Ks are orders of magnitude smaller, at least one order of magnitude smaller, that the 1K with the source should pull it up against. And if it's forwarded, I can then switch them off afterwards. So let's do that. Yeah, let's do that. And then when I know it's forwarded, then I can switch it off, because the real sync is existing. And I can leave them floating. Okay, so let's do it this way. The source. Let's just copy it. Source pull up. I need to pull up switch pin to outputs pull up. So we do pull up. So this should have fixed it. The important is that when I connect that this is forwarded, if it's forwarded, then I should not pull them up. If not forwarded, it's gone. So if it's forwarded, then I shouldn't pull them up. So this we don't care. This should not be high, but should be low. So Oh, it should be high. Well, we're in input, and if it's input now, it should be low. It means that it's a floating output, right? Let's have a look at the data sheet here. No, reference manual. GPIO, GPIO, GPIO. Where are you, GPIOs? That's flash. Clock control, GPIO ports here. CR1 here. Pull up. Okay, so we don't want a pull up. Although it would be 100K pull up, but we don't want a pull up. So we disable the pull up. Disable pull up. This also puts it in open drain. Yeah, so it's okay. And just right afterwards, we switch to input. Same here. Okay, now the detection should work better. We still didn't implement the other thing, but the detection should work. Yep. It doesn't say that they are forwarded. ITC source ready. When it's ready, it's because they're not forwarded. That works. And they are, if they are not forwarded, they're still pulled up, so this is correct. Now we also need to configure the other ones, the other pins. If it's not forwarded, and we want the master, which is here in this part. I have to see forwarded, sync not present. Let's switch on and let's see if it detects that the switch is not present. So edit information. Up, let's reboot, and normally it wants to read the edit. Sync not present. Yeah, sync not present. That's okay. Now, when the sync is present, we will be reading. So we need to start. We need to configure, and actually, oh, I don't remember which one is which one. Pin 1 is SDA, right? No. Yeah, pin 1 is SDA. Pin 1 is, where is this printout? Pin 1 is PD4. You're not seeing what I'm doing actually. No. Here. We need to configure it here. These 4 lines. Up. This PD4, and the other pin is, actually I could use the RX PD6. Let's use PA1 for now because it was free. PA1, and this is the sync, and sync. And we need to pull up these lines up. We need them when we initialize the I2C ports, which is right here. Up. No, not so far. Sync. And now we can at least use 100K. We can use even 400K to read it really fast. We will test first if it works. Think. Actually, I just needed 2 other letters. Yep. Flash. It does flash. Sync not present. That's okay. Now we will put the sync on it. I would love to have this reset button. Yeah, I'll just add the reset button. It's really useful to not have to reset using the software interface. So buttons. Where are my buttons? Here. Let me switch to the bench view so you can see my soldering. Bench. Reset buttons. Oh, and the pink is actually a lot nicer with 10K. Else it's quite white. I need to bend the leads so it doesn't fit. And let's disconnect the power so I don't create any shorts. Actually, I could use instead of the reset button, I could use the RX pin of the UART to trigger some commands. It might be better debug. But no, I won't do it. Tiny bit of gap, so I can. I'll use a reset bit button. Don't want to bloat up the code. Although it's not really too much. Come on, I don't see the other pin here. Does it make contacts? Not really. No, I did. Okay, now we have a reset button. And does it click? It's mushy. I don't feel the click. Did I break it? Does it? It's a clicky button, right? Where's my other one? Where's the one which was working? Here. No, it clearly should click. Okay, this is broken. I don't feel the clicky. Maybe it doesn't, but I just don't feel it. Yeah, this button is broken. Maybe I broke it while I was heating up. This looks ugly. you flow? Okay, now it flows. Let's get a button again and let's test it before we solder it. Maybe while bending the lead, I broke it. It's still possible. This one clicks. Let's bend it. Let's test it. This one. Okay, after bending it still clicks fine. One point soldered, still clicks. And yep, still clicks. I don't know, maybe it was just one broken button. Reset is here. So now we can test, and 1, 2. Okay, let's be sure we are at the latest firmware. It should work. Sync not present. Okay, that's fine. Let's connect a sync and let's reset and see what it does. Command sync. Monitor, you go here, and when I reset, okay, success. And actually I should make this that it reads the LED reading sync. The LED should be there before, not while it saves. Port saving. Do I want to see when it reads? Yep. I want not when it saves, but when it reads it also. Yep. Okay. Let's flash it again, and now we can always see that the LED goes on when it reads, and not only when it saves it. Come on, flash. Okay, it's again because of OBS is slow. Yeah. So you see how long it takes? It doesn't switch off at the end. Because there's an error? No, not change. There is no error. Stop success. So it should switch off the LED. Not only did we done saving when the LSO didn't change, if equal did not change, so we want to switch the LED off here no matter what. We are done. No, we don't want. We want to leave it. Where's the LED? Actually, even if I don't, even if it fails flashing, it's actually, yep. This should also be fixed. Let me switch back to full screen. Here we also want the LED go off to indicate edit is same. Okay, and when the flashing doesn't work here, we are breaking, and I want to be sure that the flashing doesn't work. EEPROM valid. I know. When it fails, EEPROM valid. When it doesn't fail, EEPROM invalid. Okay, I need to test when it is. This is some other information here. I need flash complete, flash success. Yeah. Bool flash success is equal to true, and if it works, if it fails, is equal to false. If it fails here, false. Remember we had an error. Remember we had an error. Remember. I can't write anymore. Remember we had a flashing error. And actually, I can expedite that. This is true as long as we don't have an error. Now rewrite, that's okay. If flash success, then we switch off the LED. Indicate that there's a new HDMI. Yeah, we can. Else put flashing error. Flashing error. I haven't seen any flashing errors yet, but I don't know how often, and I don't think it will be used very often. Let's compile it. The computer is so slow when OBS is running. This shouldn't take so long. I don't know why it does. Okay, it wrote. What did it say is it did not change. Okay, and there's also no flashing error. And normally if I switch off, it should tell source ready and edit is protected. Source ready. This is source ready. And now let's try to test if the forwarding is detected. Lines forwarded. Yeah, it is detected correctly. And now let's do it not when I power it using this, but when I power it using the Raspberry, which is probably not even on anymore. So easy protected and light forwarded. Yeah, edit protected. So yeah, the screen doesn't go on because the Raspberry Pi has gone to sleep. Let's switch to the bench. And normally, now, if everything is correct, now the lines are forwarded, so I'm not intervening, and this should still work. So it will read the original edit information from the original monitor. Yeah, it works. So the monitor goes on. You probably don't see it, but there's a mouse. Now it's white. Now you see it. And if I disconnect the monitor, so disconnect, I switch off the forwarding, and if I reconnect, which should still be emulating the source, the sync, and it should still work. And it does. Perfect. HDMI firewall version 2 is ready. Well, on all the cases I can test, and the firmware is complete. I need some small redesign and some, yeah, I'll just make this more compact. I'll add some, I don't know how we'll add, no I can. The lines go here, so I can add the pull-up resistors right here on the left. And then I can order a huge batch and sell them. So I think in 2 with 3 weeks or something like that, I should have a batch of HDMI version 2 and be able to sell them. Once I've tested. I don't have a big test setup. This will be a pain, testing each one of them. I can forward them, I will flash them, but I need to test if the data lines work. The other ones, yeah, I don't really require, do I? Don't know. But at least for now, the version 2 works. I'm quite happy. I found some bugs, like always. I fixed them, and I don't see any other bugs. So with that, the stream is ready, and well, see what the next topic will be. There are 2 boards I need to order now. Ooh. Okay, but you can enjoy the rest of the day because I'm closing the stream. See you. Enjoy.